All right, so this video is going to go over pages 18 and 19 in your vectors packet. Okay, so we're going to take a look at relative motion and independence of vectors. Okay, so number one, a train travels west at 25 meters per second. Okay, so we have a train traveling west at 25 meters per second. A passenger on the train walks to the rear of the train at 2.5 meters per second. So if they're walking towards the rear, that means they're walking towards the back. Okay, so that means that they are going east at 2.5 meters per second. Okay, so what does an observer off to the side of the train tracks view the person's velocity to be? So that means I have an observer over here, and they're basically seeing is how fast does that person look like they're going to the observer that's standing to the side of the train. Well, if the train's going west at 25 and the person on the train's going east at 2.5, okay, we're going to figure out what the difference is there. So we're going to do 25 minus 2.5. So it's going to look like that person is doing 22.5 meters per second. Now, we got to add direction with this. Now, if the train's going 25, the person's not overcoming that. So that means even though the person's walking towards the back, it still looks like they have a velocity of 22.5 meters per second to the west. So you can write west, you can draw an arrow, whichever one you prefer, but that would be your answer right there. Number two is the exact same problem. Okay, just be careful when we start bolding things. So on this one, a passenger on the train walks to the front of the train. Okay, so just be careful on that. Just make sure you're reading your problems thoroughly. Okay, so I've still got my train going 25 meters per second to the west. But now my person's walking to the front of the train at 2.5 meters per second. And our observer is still off to the side. And so it's going to look like that person is doing 27.5 meters per second. Okay, both going west. Okay, because now the person is on the train and you're going to combine those velocities, so they're going to be going in the same direction. Okay, number three, what would be the observer on the side of the train track's view of the person's displacement, okay, to be in the previous question in the time of 2 seconds? So one thing I've been saying in class is if we are not doing SOHCAHTOA or Pythagorean theorem, the only other equation you're going to use in this unit is V equals D over T. So the fact that they're asking for displacement and I gave you time, okay, that means we're going to be using that. So we don't need to do Pythagorean theorem or SOHCAHTOA, okay, to find this. Okay, so velocity, displacement, and time. We're just going to fill in what we know. Time was 2 seconds. Okay, they asked for displacement, so that means they're looking for the distance. And it says we're talking about the previous example, so number two. So that 27.5 is our velocity. So 27.5 meters per second. So all we're going to do is just plug in. So 27.5 equals displacement over time, which is 2. So all I got to do is multiply both sides by 2. And you're going to get a total displacement of 55 meters to the west. Okay, number four. If you're driving at 59 miles per hour, okay, so we're driving at 59 miles per hour, and a car comes up from behind you and hits you going 60 miles per hour, what speed does the other car crash into your car at? Okay, so this is where you got to be careful. On number two, on that train, we actually combine their velocities there. That's because they're on the same, the person is actually on the train. So that's why we can combine those velocities. Okay, this is not a car driving on top of another car and stuff. This is a car going its own direction, and then another car ends up bumping into it, okay, with just 1 mile per hour faster. So just picture yourself in that car. If you're driving 59 and someone comes up and bumps you going 60, we're not going to add those velocities. It's not going to feel like you're going 119 miles per hour when you get hit by that car, okay? But so what we're doing here is we're going to take the difference in that velocity. Okay, so it's going to be 1 mile per hour difference there. Okay, number five, a dog walks directly across a 30 meter wide wide ship deck at 2 meters per second. If the ship is moving forward at 8 meters per second, calculate A, the time for the dog to cross the deck, and B, the dog's resultant velocity. Okay, so I'm looking for time. Okay, so that means I got to start doing my V equals D over T. So A is going to be V, D, and T. Okay, so we're looking for time. Okay, if the dog is walking across the deck, we figured out the deck was 30 meters wide, so there's your distance. And if we're talking about going across the deck, and I'm talking about the dog, we're going to use the dog's velocity, which is 2 meters per second. So that boat's velocity has nothing to do with this problem. We're just talking about strictly going across the deck. So it's going to be 2 equals 30 over t. Be careful with your math. You can always switch the t and the 2. That is only when the variable that you want is on bottom. Okay, so if there's an x on bottom, you can do that. If it's on top, you cannot. So that means it's going to come out to be a time of 15 seconds. Now, part B, it says find the dog's resultant velocity. So anytime I say resultant, that's a dead giveaway. That means I want the combined velocity now, so which is going to be your triangle, which is going to be your hypotenuse. So part B is I'm going to have this dog going across at 2 meters per second, and the boat's going forward at 8 meters per second. Okay, so we're going to have this displacement right here that's going to look like this. Okay, so we're going to find our hypotenuse and our angle. We're not going to worry too much about direction on this one because there wasn't really a direction. So we'll just solve for our hypotenuse and our angle, and we'll worry about direction when we actually give you more direction, like east, west, north, south. So in order to find that hypotenuse, we're going to do Pythagorean theorem. So x is going to be the square root of 8 squared plus 2 squared. Okay, so don't forget to square root at the end. Okay, so that's going to come out to be 8.25 meters per second. Now that's your hypotenuse. We got to find our angle now. So our angle, what we've been doing is I have my opposite. That is your 8. I have my adjacent. Okay, that is your 2. So we're going to do that inverse tangent. Opposite over adjacent, so 8 over 2. Okay, so our angle is going to come out to be 75.96 degrees. And we're not going to worry about direction on this one. We'll just go with that angle there. Okay, so now let's actually do more practice on that stuff. So we're going to do this boat problem on number 6. And then that'll finish off this video. I have a river as 360 meters wide, and a current flows from east to west at 8 meters per second. A boat moves at 12 meters per second as it heads north crossing the river. Okay, so I'm going to draw the river. I know my river, so don't forget to label this. I know my river is 360 meters wide. My boat is trying to go north and cross it at 12 meters per second. And my river is going towards the west at 8 meters per second. So my triangle is going to look like this. So we're going to probably need to find our hypotenuse at some point and our angle. We'll worry about that when we come up to it. Okay, so for now, that is my drawing. So again, if you drew your triangle like this, so say you went left first and then down, okay, that's totally fine. Your angle is just going to be different, okay? So either way, both of our angles should add up to 90 degrees. So part A, it says, what is the time for the boat to cross the river? So did that ask for resultant? Nope. Did it ask for angle? Nope. So that means I can't do SOHCAHTOA or Pythagorean theorem. Okay, so we're going to do our V, D, and T. Okay, so what time for the boat to cross the river? So the question mark is our time. Now, if I'm talking about going across the river, my distance of the river is 360 meters. That's how wide it is. Now, this is where you got to be careful is if I'm talking about going across the river, I'm talking about going vertically across the river. I want to see which velocity is going north across the river. Well, that's going to be your boat. So we're going to use that velocity of the boat. Okay, so we do not care about the 8 meters per second. We don't care about the hypotenuse. We're just strictly talking about going across the river. So we're going to go ahead and plug in. So 12 equals 360 over t. I can swap those two. So 360 divided by 12, and you'll get a time of 30 seconds. So that is your answer there. So if you noticed, we didn't use that 8 at all in that. Okay, so that means we could change that 8 to wherever we want, and we're still going to get 30 seconds no matter what. Okay, so that's a good example of how east and west does not affect north and south. Okay, that river could be 50 meters per second, and you'd still get across in 30 seconds. Now, would you be pushed further down the river? Yes, but that didn't actually affect your time to get across the river. Part B, how far downstream does the boat land? Okay, so we're looking for how far downstream, so that's distance. So we're going to do our V, D, and T. Okay, so we're looking for displacement now. Our time, we just found it was 30 seconds. Okay, velocity, if we're talking about going downstream, I want to know what velocity is the one going downstream. That is the 8 meters per second. So now we have all of our items we're going to plug in. So 8 equals d over 30. So displacement, so it's going to be 8 times 30 is going to be 240 meters. Okay, so that's how far downriver it pushed us. C, okay, says what is the resultant velocity? So that when I say resultant, that means the hypotenuse. So now we can solve for hypotenuse. So I'm going to solve for that using Pythagorean theorem. So I'm going to do x equals the square root of 8 squared plus 12 squared. Okay, so again, just don't forget your square root at the end. So it's going to come out to be 14.42 meters per second. So there's your magnitude. Okay, now we're going to find our angle. Okay, we're going to do that inverse tangent of opposite over adjacent. So that's 8 over 12. Okay, and our angle is going to come out to be 33.69 degrees. Now you got to figure out your direction. So remember, whichever direction line the angle is touching, so it's touching north, that's got to be my last letter. Okay, so you've only got two options. It's either north of west or west of north. Well, if it's touching the north line, that has to be my last letter. So that's going to be west of north. Okay, part D, what angle should the boat have directed towards to end up directly across the river? Okay, so what my goal is I want the boat to go directly across the river from where it started. Okay, now if I've got a current pushing me downstream, that means you're going to have to head into that current, okay, to make up for that push downstream. So we're going to point our boat upstream to see if we can get across the river at the exact same point. So we're trying to figure out what is this angle right here. Now, a good question I had is why wouldn't it be 33.69 degrees, just the opposite way? Okay, is you got to think about is before the boat was just simply going across. Okay, the river wasn't hurting it or helping it. Okay, it was just simply going across. Now what we're doing is we're turning the boat partially into the current, so that's going to slow it down. So we've got to account for that. So it's not going to be the exact same angle. Okay, because now we're changing the direction of the boat. Now, we didn't change the speed of the boat, still going 12 meters per second, but now that's my hypotenuse instead. Okay, so now it's converted to my hypotenuse. My river is still to stay the same. Okay, that's still 8 meters per second. That is my opposite. So I'm going to see which of my three trig functions has opposite and hypotenuse. Well, that's going to be sine. Okay, so sine of your angle equals opposite over hypotenuse, so 8 over 12. We're going to bring this sine over. Okay, and that when we do that, it becomes inverse sine. Okay, so real quick before I solve this, is the only time you ever do inverse of any of your sine, cosine, tangent is if you need to find an angle. Okay, just think about this sine and the angle are like a package deal. If you take it off of there, you've got to change it somehow. Okay, so if I had something like this, let's say I had my angle, sine of 30 equals 8 over x. Okay, well, I know that algebraically I can just switch these two. Okay, so that would be x equals 8 over sine of 30. So that's all you got to do is just take 8 divided by sine of 30. So if you noticed, I didn't make that an inverse sine just because I brought the whole thing over. Okay, because I already had the angle. Okay, so don't make inverse sines or cosines or tangents unless you're looking for an angle. Okay, so just be careful with that because I know sometimes if you see it happen once, okay, then your instinct is to make it go inverse anytime you move it at all. So we're going to find inverse sine of 8 over 12, and we're going to get an angle of 41.81 degrees. And our new direction is it's touching the north line. Okay, so that's got to be my last letter, and it's going east of it. So this is going to be east of north. And that'll end that one.